running a seminar series to happen every other Friday starting this week. So for all those interested, you can come in and just listen to a bit of the things we're working on or that our collaborators are in topics. I had YouTube open for questions and then it just started talking at the same time. But the idea is that we have the seminar starting today. And for people who are curious and who want to know more, we have already published the agenda for the next seminar. So you'll be able to see who's incoming over the next few weeks as we post the names. So today I'm happy to introduce Gregory Stein. Greg is a close friend I've known since my PhD years. And basically, he's an assistant professor at George Mason University in computer science, where he's working on robotics, machine learning, and developing representations so robots can plan their actions better. It's been published in so many different conferences in robotics, machine learning, just from ICRA to ICLR to NeurIPS to many others, and is a very big voice in the robotics community. So I want to bring Greg to just tell us what he's been working on. I will be monitoring Zoom and YouTube for questions. So any questions, Greg, do you want us to interrupt you with questions, or do you
interrupting is totally fine, right? So, if you have any questions, especially because I'm definitely more of a roboticist and I know this is more of a mathematics-y audience, I tried to keep this talk self-contained as best as I could. But if you still have any questions, whether it be about the research or whether it be about robotics in general, please do not hesitate to ask. I know there are a lot of students here. I love pedagogy. I love teaching. So definitely feel free to interrupt and ask things.
Sounds good.
Okay.
So please feel free to start whenever you're ready.
Great. Thanks, Lucas. And thanks, everyone, for having me. It's really great to be here, if virtually, although I would love to come visit. Hopefully, our ICLR paper will get accepted and I can come to Brazil. But yeah, so today I'm going to be talking about a lot of my work that is at the intersection, as Lucas mentioned, of robotics, machine learning, and planning. I do a lot of planning and decision making. So I'm generally interested in this big picture vision, as are many roboticists, with this idea that robots are going to be expected to complete complex objectives in homes, buildings, hospitals, offices, etc. Everything from tasks that involve telling a robot to do things like load objects into a cabinet. And so we have our Fetch robot. It's a mobile manipulator, so it can move around the world, and it has a gripper arm that it can use to pick up objects and move them around the world into this makeshift cabinet that we have. To the more complicated and intricate tasks that involve things like preparing breakfast, or the multi-stage objective that includes things like making the bed, restock the shelves, and then bring breakfast. The robot has to do many different things and interact with many different objects in the environment in order to be able to complete these objectives. There are, as you might expect, many different approaches that can tell a robot, here, do something, and then the robot, with its own understanding of the things that it can do to interact with the world, can then sequence those actions into some kind of plan. There's even a programming language. There are many of these programming languages, but one of the most popular is known as PDDL, the Planning Domain Definition Language. It is a Lisp-like language, so for those of you who have any training in classical AI or an Emacs user like me, you're familiar with Lisp. Lots of parentheses, but the short version is that I can express this goal that I might say in natural language as load these objects into the cabinet, and the goal can then be expressed in code as a union of a bunch of Boolean operations. This over here says that all of these things must be true. The red block is at the cabinet, all the way down to the blue block number 2 being at the cabinet. So all of these expressions are written like a verb and then a bunch of nouns. So it's kind of a weird syntax. It won't come up too much in this talk, but it's just something to be familiar with. If I tell the robot all of the different things that it can do, like move around, pick up objects, place them in different places, then the thing that I might get out of this system, as long as the robot knows the different things that it can do to affect the state of the world, is to come up with some kind of plan that's a sequence of these actions. The robot moves to the table, it picks up blue block number 2, it moves to the cabinet, it puts it down, and so on and so forth until this goal specification is met. So there's a lot of work in this space of what's known as task planning, and many established approaches to solve them. However, and perhaps this might surprise you if you've never worked in this space before, but many of these approaches are only supposed to work, they're intended to function only when the robot has full knowledge of the environment. And yet, robots are going to be expected to complete complex objectives under uncertainty. When placed in a new environment, the robot may not have a map and must search for task-relevant objects. Even when placed in an environment that the robot is familiar with, that it has seen, maybe it knows where the kitchen is, maybe it knows where the dining room is, most environments are dynamic. I, as a human, live in these environments and I'm constantly moving these objects around. If I tell the robot to find my water glass or to find my keys, they are not reliably in a fixed location. As soon as the robot doesn't have full information about the state of the world, most approaches to planning fail. Because in order to synthesize some kind of plan like the one that we showed, whatever, 2 slides ago now, the robot needs to have enough knowledge to be able to say exactly what will happen and exactly when it will happen. As a result, they can't necessarily make good decisions when placed in these unfamiliar environments or even familiar environments where they lack any piece of information about the world. Suddenly, these tasks, these open-ended objectives like preparing breakfast or making a bed, restocking shelves, and finding a nurse, as you might need to do in a hospital domain, become quite a lot more complicated because the robot now needs to make judgments about what it knows and what it knows it doesn't know in order to be able to make effective decisions in these open-ended challenges in these difficult environments. And to give an example of why this is so hard, and not just motivate, well, there don't exist tools, I'm a programmer, I could write a tool if the answer is relatively obvious, I want to motivate this idea that even point-goal navigation, getting from point A to point B, can become incredibly challenging when you don't have a map of the environment. So imagine this scenario where you put a robot in an unfamiliar building and you tell it to get to some objective that's roughly 100 meters away. It's kind of out and to the left. What would you do? Well, let's look at what a robot does. If the map is known, this navigation problem is relatively simple. There's a lot of knowledge in this. There's a lot of, like code bases and things that can do motion planning, coming up with some kind of trajectory that goes down the hall, makes a left at the bend, and then continues on to the goal. The challenge, though, is that when the map is not known, the robot needs to reason about what it's going to have to do when it leaves known space. This is hard because imagining the future is hard. And I know that's kind of a simple statement to say, but when it comes to this particular sort of planning problem, most robot planning approaches need to resort to simple baseline or fallback strategies when the map is not known. The sort of optimistic approach assumes all unknown space to be occupied. It's optimistic because it says, well, I'm just going to assume that I don't see any obstacles in unknown space. But the problematic behavior here is that the robot ends up making an early left turn into what you and I might recognize to be a classroom and maps this entire classroom before realizing it's a dead end, turning back around, going back to the hallway, and then making more progress to the goal. And it gets stuck in a few classrooms and even closets along the way because it lacks the ability to understand what lies immediately beyond its observed surroundings and farther than that as well. This idea of optimistic planning is a relatively simple strategy, and it's convenient because of its elegance and ease of implementation. But in general, this optimistic agent, this robot that makes a naive assumption about what exists in unseen space, unnecessarily explores many classrooms and offices and closets, this is behavior that is decidedly unhuman. You would never go into a building and just start entering everybody's office in search of some faraway objective. You explore with intention. You understand the way that the environments are laid out. You know that hallways are designed as structural features to connect faraway points in space. And so following a hallway is a really good way to travel long distances in these indoor environments. So let's keep this in mind and understand that our intuition is a very difficult thing to translate to a robot, which thinks differently than us. It relies on code and precision and a precise understanding of exactly the state of the world. And keep that in mind when we now think more about these planning under uncertainty tasks for something like meal preparation. Now, preparing breakfast becomes quite a lot harder. In the same way that this idea of naive, optimistic navigation has the robot entering all of these classrooms and closets and things that it has no business being in when the goal is sufficiently far away, the robot now needing to look for objects of interest will start looking absolutely everywhere. If it starts in the bathroom, it'll start looking in the bathroom. Except if I tell it to find a fork, that's probably a bad place to be. What we should do in these sorts of planning under uncertainty scenarios depends on what objects we think exist and how easy it's going to be to find them. The approach that we take to complete this rather difficult objective requires nuanced, long horizon reasoning to yield plans that jointly search, interact with objects, and when necessary, actively gather task-relevant knowledge about the environment. Think about what you would do if told to prepare a meal in someone else's kitchen. The first thing that you might do is look in the refrigerator and look in the pantry, because the knowledge that you get from looking in those can then help you understand how to plan more effectively. So this is information gathering. It's shockingly hard because in a robot, it has to imagine what it might get when it opens the refrigerator and then what it might do with that information. Sort of like one might think of playing chess, as imagining a bunch of moves in sequence. It doesn't scale very well. It doesn't work very well. Now, the sort of elephant in the room, and I'm going to use this elephant to my advantage, is this idea of learning. Learning can help us understand what might be in unseen space. Things like ChatGPT, large language models, and their related family of capabilities, often referred to as foundation models in the robotic space, can indeed generate some reasonable candidate next actions. So it can say, okay, here's some reasonable things I might do. But in general, large language models are not very good at math. And as a result, they're not very good at coming up with effective actions. They can say, here's a bunch of things that might be reasonable next steps, but cannot do a very good job of solving these very complicated objectives with many steps and coming up with an effective plan that makes quick progress towards them in these large, open environments. As such, using these learned models, large language models like ChatGPT or these foundation models in general, directly to try and say, here, robot, do this action next, frequently results in unreliable or myopic performance for these long horizon planning under uncertainty objectives. Now, the thing is, I've now presented two different possible solutions that each have their relative disadvantages. Planning is particularly effective at just sequencing actions, just like playing a chess game. If I know what moves I can execute, if I know what moves my opponent might execute, I can imagine how a sequence of moves can be better or worse compared to another. However, the lack of understanding of what lies in unseen space holds that back. And so instead, a lot of the work that I do in my lab seeks to leverage the strength of both learning to help us reason about uncertainty and planning for effective and reliable long horizon decision making. So let's revisit this idea of the point goal navigation scenario. Rather than thinking like a robot does in terms of trajectories, which in human language might be, I put my left foot forward and I put my right foot forward and then I put my left foot forward again. That's not how I think about making decisions in these long horizon tasks. When I'm thinking about building scale navigation, instead we think at a different level of abstraction. So rather than thinking about these individual motor commands, steering wheel commands, and everything at that very low level, instead we want to represent the world in some simplified or compact manner that lets us think farther into the future. So in some of our work, we introduce a high-level action abstraction for robot navigation. The actions that the robot can decide between are no longer at the level of steering wheel angles and speed and motor commands, but instead they each correspond to exploration of a particular region of unseen space to try and find a route to the goal. This idea of coming up with an action abstraction is a very useful way of thinking about robot planning. In the same way that when I told the robot to pick up a block and asked what will happen when it's done picking up the block, the answer is it's holding the block. It's not all of the different motor commands, joint angles, and metric positions of where that block is located in space. I instead have some sort of symbolic or abstract representation of the state that I can use to think farther into the future. When it comes to thinking about this navigation case, though, we now need to also think not just about what the robot can do, but what might happen when it executes these actions. So for each one of these high-level actions, we can also reason about these high-level or abstract outcomes. Namely, that when I enter this classroom over here on the left, because the goal is so far away, it's very unlikely that this action is going to lead me to the goal that I seek. By contrast, as I'm sure your intuition tells you, following the hallway is much more likely to lead me to this faraway goal. We refer to these as exploratory actions. Each one of these is a high-level way that the robot can leave the partial map of the world and try and reveal some part of unseen space beyond what the robot knows in order to try and make progress towards its objective. In this case, reaching some point in unseen space, some like GPS coordinate where I'm meeting someone or picking up a package. So in this particular case, this partial map shows that the robot has three possible exploratory actions. Action number one, in particular, has the robot navigating to this boundary and then exploring the space beyond in order to try and reach this unseen goal. Now, given this action abstraction and the things that we think might happen and how likely they are when I explore each one of these regions of unseen space, it is tempting to think that the robot should go to the most likely option. Just do the thing that it thinks is most likely to succeed, and then call it a day. Keep doing that every time it updates the map, make more predictions about which action is most likely to succeed, and keep going. But whatever, fortunately or unfortunately, that's not how the world works. If I want to, let's say, prepare breakfast for somebody, I don't know what's in their refrigerator. Maybe there's a 50% chance that they have eggs, and I want to make them eggs. I know with 100% certainty that there are eggs in the store down the road. But I should probably look in the refrigerator first, even though it's less likely to succeed, because overall, the thing that I care about is cost. I want to perform well. And reasoning about cost is the thing that is the reason why ChatGPT is not very good at solving these sorts of problems. Is because I don't want just a reasonable or likely thing to do. I want the best thing to do. And to understand what best looks like, we have to introduce what is referred to as the Bellman equation. So this is now one of my only math-heavy slides in the talk, but this is meant to build some intuition about how robot planning problems unfold. So when I think about giving the robot a task, I want it to try and minimize expected cost. This thing over here is known as the Q function. It takes in two arguments. It's the robot's belief. That's the partial map of the world. This is what it knows about the world and what it thinks it knows about the world, and some action. As I introduced in the previous couple slides, I said that the actions corresponded to where the robot can explore. So either action 1 over here, action 2, or action 3. Now, in order to evaluate how costly or how expensive that action is, I need to just play out in my mind some model of me imagining what happens when the robot tries to execute that action. The first thing that the robot has to do is travel through known space. That's easy. I already know how to navigate through known space. I mentioned that a little bit earlier. The robot drives down to this boundary that corresponds to the exploration for action number 1. And it accumulates some cost that I write down here as a distance function. It's just the robot driving from where it started to the boundary itself. Now, what I said, looking at this from the perspective of these high-level actions and outcomes, upon reaching the boundary, the robot then tries to explore the space beyond, and one of two things can happen. With some probability of success, the robot succeeds, and it reaches the goal and accumulates some expected cost associated with traveling in unseen space to try and find the goal. But with some other probability, it fails and it's forced back into the environment. It explores a little bit and it accumulates some cost of actually exploring that environment or that part of the environment, just like the robot that entered the classroom had to move around a little bit before it realized that it was a dead end, and then comes back into the hallway before continuing and exploring another action. I say hallway here just to give an example. These can really be any parts of the environment. And in fact, in this formulation, the robot is making no particular judgment about whether the part of the environment it's looking at is a hallway or a classroom or whatever. Now, upon failing, the robot needs to then do something else. What does it do? It executes another action. The Bellman equation is evaluated recursively, and this should make sense. When the robot is done, when it has failed with some probability 1 minus the probability of success, it accumulates some cost of exploration and then needs to pick another action. From the perspective of the planner, by the time the robot fails, this now planning problem looks like another iteration of this planning problem. The robot has now ruled out that this action can lead to the goal and now has to pick between one of the 2 remaining actions, and so on and so forth. Like playing chess, the robot is imagining what it might do, what might happen as a result, and so on and so forth, all the way until it has exhausted every possible option available to it. And the objective implicit in this equation is to try and find the action that is best, that minimizes expected cost of navigating through this environment. Now, the robot should pick actions that are jointly likely and low cost, and help it broadly make progress towards the objective. Now, you might be asking yourself, well, where in particular does this probability of success come from? And because this involves navigation in the unseen part of the environment, where do these costs come from? The answer to that is learning. The robot is going to use its experience in similar environments to try and predict or anticipate what might happen. And as a result, we refer to this as our learning over subgoals planning abstraction. The learning is the thing that tells us how good it's going to be to explore different parts of unseen space. And this we use to instantiate a planning problem and then help make decisions about how to navigate in these environments. As a result, the robot is able to generally travel or prioritize based on its understanding of how the world works paths that are much more likely to reach this unseen goal. And so the robot we have over here is running our algorithm, which is making predictions about what parts of the environment are more likely to lead to this unseen goal. And the robot has a tendency to stick to hallways because that's what its experience tells it. When the goal is far away, it should generally stick to hallways. In these simulated environments as well, we can see very similar behavior. The robot occasionally peeks into some of these classrooms because some of these classrooms have multiple doors, and that's actually not a very bad strategy. But for the most part, the robot has learned to avoid a lot of these dead ends. And so it identifies these features that lead to the dead ends and can generally avoid them in order to make quicker progress towards the objective. This learning over subgoals planning abstraction has some really nice features. It allows us to approximate a very challenging planning under uncertainty problem as a far easier stochastic Markov decision process. If you've never heard that, it's kind of technical jargon that says what class of problem we find ourselves in. But the interesting bit in particular about this, and things that continue to guide my research, even whatever, 6 years after we first published this paper, is this idea that learning is only used to make predictions about uncertainty. And this contrasts our approach with a lot of more modern approaches that continue to use learning to replace planning. We are still using planning to help sequence actions, to make decisions about what the robot should do, and the learning is only there to help us fill in the missing pieces. So when the world is fully known, learning is not used. The key idea here is learning augmented model-based planning. Learning is used to estimate parameters of a model, but planning itself is classical. It's still basically playing some kind of chess game. And so we're planning without any reliance on learning whatsoever. So we're doing that thing that I mentioned earlier, benefiting from the strengths of both of these styles of approaches, planning and learning. So as you can imagine, this was some earlier work that we did in this space that focused in particular on navigation, but since then we've done a lot more complicated problems. Since then, we've done things like effective and reliable task planning under uncertainty. We have some objective here expressed in some predicate language known as temporal logic or linear temporal logic. This is just Boolean logic with time added as some extra operators. What this basically says is that I want to put out a fire in some simulated environment. And we can do that either by finding a fire extinguisher and then using it to put out the fire, or pulling some building-wide sprinkler and spraying the whole building with water. Now, rather than just thinking about ways that the robot can reveal unseen space, we're trying to combine our new methodology that says you have these exploratory actions that can leave known space in search of the fire and the sprinkler or the extinguisher. Or you can use the actions that the robot already knew it had when it was thinking about just planning in known space, that it can use to interact with entities already observed by the robot. This idea being that the robot already knows where the fire extinguisher is, it should know that it can use it rather than just looking in unseen parts of the world. This general abstraction that we have of trying to make predictions about the outcomes of exploratory actions while also benefiting from 50 years of research in robot planning for fully known environments has really been a key enabler of a lot of progress in my lab. Our approach has enabled effective long horizon reasoning under uncertainty across many planning applications. Things ranging from exploration. How can I, with a limited battery life for a limited amount of time, reveal as much of an environment as possible? Over here, actions correspond to revealing space beyond each one of these boundaries. Planning seeks to maximize the amount of space the robot has seen within some predetermined time limit. And then we're also doing some this is like ongoing work. We're submitting this in just another couple weeks. We've been doing some really complicated task planning scenarios like the ones that I promised at the beginning of the talk. This is one of those. We have also the work in progress results in the breakfast scenario, and unfortunately I can't show you figures for that yet. We have a physical spot robot, one of those big like $200,000 robots that's moving around the environment and making breakfast and pouring cereal and doing all sorts of cool stuff. But for now, you'll have to settle for this find and retrieve 3 objects scenario. The robot is being told you have to find these 3 objects and place them in different locations throughout the environment. The optimistic versions over here, and there's some variants that I'm not going to get into, just kind of start looking around the environment. They just start opening cabinets and looking on tables and doing all sorts of silly things that humans wouldn't do. By contrast, you can help the robot by saying, well, here's where these objects might be. But the really challenging thing is knowing not just where those objects might be, but the order in which you should look for those objects. Because if I'm already in the bathroom and I need to find something in the bathroom, I shouldn't leave the bathroom to find something in the kitchen and then come back. So our planner, which is shown here on the left, has a very parsimonious, a very sparse path that shows that the robot is looking for a few of these key objects and does a really good job of effectively using its space to navigate this environment. It's not quite perfect, But that's expected because the robot doesn't have perfect observability over the environment. It's not looking in some places that are lower likelihood to contain those objects and then goes back to try and find them when it can't find them anywhere. Tell me the number of times you've lost your keys only to realize they were right next to you in the first place, but your plan was not necessarily a bad one because you went and you prioritized places that were more likely to contain those keys. And you did that all while getting ready in the morning, right? You got dressed, you prepared your breakfast, you got your keys, very complex set of objectives. And our planner is one of the only things at the moment that is really capable of taking this very complicated, long horizon objective and coming up with an effective plan that balances reliability, because we are using a planner and 40 years, 50 years of research in robot planning and decision making, while trying to improve the performance of those algorithms by making predictions with learning. We can also do those things. Remember I mentioned looking in the refrigerator? This idea that you could execute information gathering actions. We have a couple papers in this space of active information gathering as well. It's a shockingly hard problem. And this is kind of a simple prototype of what that might look like. This paper was published last year in IROS, and you can take a look at it if you want. This paper I really love this paper. It's kind of a niche problem, but it was really interesting. There's this really I don't know if you ever go to a building you've never been in before, and then, you could start wandering around and looking for somebody's office. But the best thing to do typically is to go look for a map. So you find the elevator, you find a staircase, and you find a map of the building that firemen might use in order to respond to a fire in the building. And that tells you exactly where to go. This is exactly that, but for the robot. The robot is capable of going out of its way. It decides when it is best to look for a map. And then it goes and looks for a map of the environment in some security office in this simulated environment, and then it can navigate much more effectively. Some of the things that I'm really excited about lately, and I actually have a couple grants from the United States government, because that's how a lot of academic research is funded here, on multi-robot decision making. This work is a little bit old, actually. In fact, some of the newest work that we're doing is some of these breakfast preparation scenarios with 3 robots in the same environment at the same time. They split up. They navigate different parts of the environment to reveal the map. They find objects collectively. And more recently, we're starting to think about robots can work as a team, both working on trying to reveal parts of the environment while also lifting heavy objects together and all that sort of stuff. So we're constantly trying to make this more featureful, but the underlying idea, the underlying abstraction is shared. It's similar between these different planning scenarios. That core idea of these learning augmented planning abstractions means that we can imagine what each robot is going to do at each time into the future and predict how each one of their actions is going to reveal unseen space. Robots engage in these exploratory actions while also making progress towards tasks in the fully known parts of the environment, and so on and so forth. The centrally coordinated team knows to split up and cover the environment for an entity of interest, guided by the predictions from a learned model. Now, for those of you with any experience in learning or some armchair knowledge of machine learning, you might be asking yourself, well, Greg, what is doing the learning here? You keep saying you're doing some learning, but what do you use as an input? Well, the good news here is that our abstraction actually makes it so that it doesn't really matter what your input is. So going back to this equation from a little bit earlier, scrolling back, the thing that I basically said is you just need some way of estimating the relationship between your partial state of the world and some prediction about how likely and how costly your actions are to succeed and how costly it's going to be in order to actually execute them. As a result, I just need some way of mapping knowledge, my partial knowledge of the world, into some learned algorithm and then making predictions. We have a number of different papers that explore a variety of different options. Some of the things can take in images. We have a lot of work that uses images. A robot takes a picture of a classroom and I ask it, how likely is this classroom to lead you to the faraway goal? And it knows from experience that the probability is very low. We can use things like graph neural networks and transformers, but then more recently, we're also thinking about using things like ChatGPT. The problem that I said with ChatGPT was not that it doesn't contain some of the knowledge that we need in order to make good decisions. It was that the ways that ChatGPT tends to process information is very ineffective for solving these really complicated planning problems. As a result, we let our planner, the decision-making algorithm, make the decisions, but we use ChatGPT to make predictions about unseen space. That decomposition has proven very effective. It leads to better performance and also a reliability that ChatGPT does not have. Any questions so far? It's kind of a whirlwind tour of a lot of the work that my lab does. And but the next phase of the talk continues to dive deeper on this.
So I'm going to ask one question.
Yeah.
How do you know your set of actions that you can take in a given position?
It depends a little bit on the sort of environment. I've talked a lot about navigation, where I say, like, the boundaries between free and unknown space. Each one of these boundaries that I show over here corresponds to a way that the robot can leave known space and try and find a path to the goal. In this case, the actions are coming from some processing step on the partial map. But in this known space case, or in this like task planning case, my actions correspond to like cabinets I haven't opened, tables I haven't searched, rooms I haven't searched. That's the exploratory actions. And then the known space actions come from my object detector. I look at objects that I have seen and then say, well, okay, that's a water glass. I can pick it up. I have some skill that I can use to pick it up. There is a lot of implied understanding. I mean, and this is like robotics is such a big field. There's always so much. Like when you run a robot, it's running like 100 processes at a time. We're also assuming right now that any of these high level skills, like pick up the glass, are things that the robot can do. Like it knows that when I tell it to pick something up, it has some process that's going to run until the glass is picked up. And we take advantage of that. In fact, a lot of research in robotics focuses on those skills because it's still kind of an open problem how to really reliably manipulate objects, interact with them, push buttons on a microwave. It's very, very hard. So we leverage a lot of that progress in like being able to navigate, being able to pick up objects, and then try and sequence those actions into some kind of policy that then allows the robot to make effective decisions. But yeah. All right, cool. So far, we have assumed that our training and test environments were similar. Again, if you've played around with machine learning, you know how important it is to make sure that your test time data is the same as your training time data, because these sorts of algorithms don't really generalize very well, as much as people might want to try and convince you otherwise. As a result, when we train in some set of environments and deploy in a very similar environment, it does great. But if we deploy in some environment that's really different, it doesn't do very well. So imagine a scenario that actually tries to evaluate this. Let's say I have the robot and it has 5 different learned models. Each one of them are trained in different types of environments. One is trained in indoor environments, one is trained in outdoor environments, one is trained in hospitals, offices, classrooms, you name it. Each one of these policies makes different types of predictions because they are trained in different types of environments. When deployed, so I buy a robot and it comes with 5 of these. I want to deploy the robot and have the robot figure out for itself what type of policy or which one of these predictive models it should use in order to be able to perform best in the new environment. So if I buy a robot with all of these different policies, it should deploy in a hospital and say, aha, this is a hospital. I should use the policy that works best in hospitals. Now, nothing is ever quite that simple. And that sort of guesswork might get the robot in trouble. The problem as well is that I can only deploy one of these policies at a time. The robot has 5 different learned models. I can't deploy all 5. I can only deploy the robot with one of them. The robot tries to execute the task, and then it sees how well it can do. Now, this is something that you as a human are pretty good at. You can look at some plot like this, and immediately you say, yeah, this was bad. I did very badly. But you can look at the one that's over here on the left and say, well, there really wasn't even an opportunity for me to have improved my performance. And so this ended up being a very good choice for how to navigate through this environment. Now, keep in mind, this is a very difficult problem, in part because even when the robot is done navigating, it doesn't have a full map of the world. It's using the partial knowledge, or at least what we would like to do, is for the robot to be deployed in a new environment, explore that environment using one of these, or accomplish some task in this environment, like preparing breakfast or finding a nurse or restocking shelves. And then when it's done completing that task, it asks itself, how well did I do? And how well might I have done if I had done something else? This is an idea known as counterfactual reasoning, and it's very, very difficult because it relies on an understanding of how the world works. In order to be able to ask some kind of question, how well would I have done if something had been different? You really need to deeply understand the way that the world works. Now, most robots don't, and I'm going to tell you how in our lab we're trying to come up with an approximation of that sort of process. To do so, I'd like to introduce the upper confidence bound bandit. It is a classic exploration versus exploitation selection strategy. This is a problem known as model selection. I have 5 different models, and I want to know which one of them is best. And I can only deploy one of them at a time. This here says which model I should take as a function of how well that model has done so far and my uncertainty about how well that model is doing in general. This is known as the trade-off between exploitation and exploration. So I want to minimize the mean performance so far and also have some bonus that says if I'm very uncertain about which model performs best, I should select that because the more knowledge I get, the more I can reduce the standard deviation in the mean. So does that generally make sense to people? I think this is a very math heavy audience. So this is the thing we're trying to do. I'm trying to pick these models one at a time to deploy. And each time I deploy them, I learn something and can do a better job of picking the next one. The problem with these upper confidence bound selection strategies is, well, they're theoretically optimal. So like this nice, so they're asymptotically optimal, I should say, so that as we continue to explore, eventually I will converge to the best performing strategy. And there's some nice proofs on, under certain conditions and the distribution over types of environments and costs and things, I can pick the thing that's going to perform best. But unfortunately, if you look at the x-axis over here, after 100 trials, the mean performance still hasn't reached the best case scenario, still hasn't reached the oracle. And so even after deploying my robot in 100 hospitals, I don't know which of my models is the best. So the robot is being deployed in an environment, the environment is being reset or randomly configured a little bit, and I'm still going and going and going. But the good news is that we have talked about how our model for planning under uncertainty can help give us some insights into how well I would have behaved had the behavior changed. So what we're trying to do here is say, look at this deployment. This deployment went really well. I started over here, I followed this green path, and I ended up at the goal. Instead, I can imagine what would have happened if I followed some policy that doesn't like the green path very much. It deviates from this path, and it underperforms. Now, I can't fully simulate exactly what would have happened in the scenario on the right over here, but I do know that it would have been worse. That information can be used to come up with some bound on performance that can be used to constrain model selection. And as a result, I can compute lower bounds on this cost in order to be able to select more quickly. So here's how this process works. We refer to this as offline alt policy replay. This was not my favorite title, but we got this paper reviewed twice, and that was what the reviewers ended up liking. So sometimes you're at the mercy of the reviewers when you're getting a paper accepted. So we deploy a policy. This did okay. This robot eventually reached the goal, but it did explore a few of these offices unnecessarily along the way. So what do? We use our model, the same model that we used for planning under uncertainty in the first place, and we can imagine how any one of our learned models would have done. And you can look over here. According to the robot's imagination, the simulation of how this policy might have behaved, policy pi 3 is the best over here. This robot goes straight down the hallway, makes a left, and then keeps going to the goal, achieving almost optimal performance according to the map that we revealed. As a result, the next time the robot is deployed, it should pick policy pi 3. And this process repeats over and over again, the robot accumulating all of the information from all of its deployments and all of its simulations in order to do a better job at simulating like how it might have done and then picking the model that is best according to the information that it's gained. With these upper confidence bound bandit approaches, it is unfortunate that they basically don't reuse any of the information they get along the way because they're not designed to. These model selection approaches are designed for much simpler problems. Our problem is more complicated, which means that they're more expensive to evaluate. But because we can actually simulate how the robot would have navigated had its predictive model changed a little bit, we can gain more information out of a single trial than is possible in general for these family of approaches. As a result, because we're capable of reusing a lot of this information we get during navigation, this darker purple line represents the performance of our approach, which very quickly converges after only about 10 or 20 trials to the best performing case. And it approaches this, like dotted orange line. And so the area under the curve, in this context referred to as the cumulative regret, is 85% lower with our approach. We do much, much better and much more quickly can pick the approach that is best suited to perform well in these sorts of environments. So we have a few different papers in this line of work. In fact, we're working on another. That's what we're submitting in like 2.5 weeks to ICRA, all this stuff constantly going. But this is like generally related to a larger form or to a broader context of research in my lab on reliability. I think that it is not enough to merely deploy these systems. We train them in some environment. We say, yes, we expect this is going to work very well. And then we deploy them in the wild. That doesn't make any sense. Users have no confidence or should not have any confidence in the ability of these systems to perform well. And so I have an entire line of research in my lab that is devoted to not just deploying robots and hoping that they do well, but also imbuing robots with the ability to look inward and ask themselves, how well did I do? And then use that information in order to be able to do better the next time. So they're constantly learning online and using the information they get to improve themselves. In the final, 10 minutes of this talk, I think that's okay with the time that I have allotted. In the final 10 minutes of this talk, I'd like to change gears a little bit and tell you this Well, uncertainty takes many forms. So far, most of what I've talked about has been uncertainty in space. This idea that the robot is starting in an environment where it doesn't know what the world looks like, and so it must wander around in order to be able to reveal things while it's also trying to make progress towards the task. And that's been my research direction for a long time. I really love that sort of thing. I think it's really important. Robots, humans encounter that sort of scenario all the time. But in the process of trying to understand what the more general framework for my lab and what my lab's vision is as I go up for promotion in another year, is this idea that there's also uncertainty over the future. Now, again, we're humans. That feels super obvious. But it raises some really interesting questions about how we even represent the goodness or the sorts of tasks that we want robots to accomplish. So far, in all of the tasks that I have given you, they've been in these kind of simulated scenarios. Even the ones that were in the real world, and I put air quotes, but I don't know, we have physical robot experiments. We have robots that are loading cabinets. We have robots that are doing things like breakfast preparation, that are looking for objects and bringing them to me in real office spaces. However, that's not the end of the universe. When the robot is finished with a task, it's going to be given another. Humans need to then live in these spaces. And to give you an example of why this matters, I'm going to revisit this idea of the cabinet loading scenario from before. We want a robot to load objects into a cabinet. Simple. The red blocks already start with these red, they're like mugs, water bottles, already inside the cabinet, and the robot needs to bring the other objects inside. So the robot does that. I tell it to load the cabinet. Now, how do we feel about this solution? We have loaded the bowls and the mugs into the cabinet. I'm going to take a little straw poll, thumbs up or thumbs down in your chat or whatever on Zoom, if you think this is good or bad. And I'm going to take a sip of water to rest my voice. What do we think? No takers. Normally, see, if this were in person, I'd ask for a continuously valued thumbs up, right? So like -1, +1, and somewhere in the middle. Right. I see a down vote from Lucas. I'm not going to put him on the spot because I've lectured him about this before. Here's the thing. Has this completed the task? It did the thing, right? But the lecture that I gave just moments ago was this idea that this is not the end of the world. Imagine now that I ask you to unload the bowls. That's now a problem because this bowl back here is obstructed by the mugs in the front. Now, I've taken the ceiling off this cabinet for visibility purposes, but the robot can't just reach over and remove it. It has to go in through the front, and as a result, it has to move these mugs out of the cabinet to get the bowls and then put them back in. The challenge, in fact, is that most robots are problematically myopic. In the same way that robots struggle to reason about what lies in unseen space, so too do robots struggle to realize the impact of their actions on an uncertain future. The robot doesn't know what it needs to do next. Even if it's told, here's like 10 different things you might be asked to do next, that becomes then a really difficult planning problem. The robot now needs to imagine how every single one of its actions might impact every single one of the things that it might need to do later on. And that's so expensive and problematic. But if the robot were able to anticipate what it might do, and we refer to this as anticipatory task and motion planning, the robot can be told, you need to load the cabinet in a way that makes future actions easier in general. The robot can be told that it needs to load the cabinet like this, so that when told to unload the bowls, that task is very simple. The difficulty here is how do we actually convince the robot that it needs to perform this sort of operation? The answer to that, as you might imagine, is learning. We can estimate the expected cost, how much it's going to cost to then do something else in this environment. It's a mapping that relates the current state of the environment to some usability score in units of cost that says now, if the robot were to leave the environment in this state, it would be much harder to do future tasks. But from this state, subsequent tasks are made much easier. We refer to this as anticipatory task and motion planning, where we use a learning to anticipate and avoid these sorts of side effects, and so with just a small amount of additional computation can be used to improve overall performance for sequential task and motion planning. Now, because future tasks will not be known in advance, instead we have some probability distribution over future states and future tasks, things that the robot might need to do later on. We can estimate some expected cost associated with starting with some state and then trying to accomplish any of these tasks that are drawn from this task distribution. The way that we then solve this problem is by running a planner multiple times. We start with some initial state. We imagine solving this task, let's say 50 times in some parallel process. And then from these 50 solutions, we pick the solution that is not best with respect to right now, that is not cheapest with respect to just the immediate task, but is best with respect to the sum of the immediate task cost and the expected future cost as estimated by our learning. What that means is that the learning is helping us pick solutions that are better not just with respect to completing the current objective, but also make sure not to make the world worse for the purposes of completing future objectives. So we pick this plan that minimizes total cost, and then we use that as we're solving this objective. What this means is that from some initial state, the myopic approach, the one that does not anticipate, it doesn't look into the future, the results show that we have relatively poor performance here. So even after giving the robot, let's say 10 tasks in a row, so load these things and then set the table, and then put them back in the cabinet and then set the table again over and over and over. The cabinet starts off kind of messy and it stays messy because the robot doesn't understand what not messy looks like. It's constantly putting objects in the cabinet and completing the task, but doing so in a way that makes future loading and unloading operations much more difficult. By contrast, our anticipatory planning approach knows that whenever we load the cabinet, we should do so and try and put the cabinet or organize the cabinet in a way that means that future tasks become easier. You'll notice that this just looks like organization. We take objects that are the same and we put them together. The robot's not told to do any of that. This is emergent behavior that comes from an understanding of how the world works, of how the robot may need to interact with the environment later on. And so it biases the robot towards better behaviors. And this cabinet scenario is a really easy to visualize example of that sort of betterness. What you can see here is that even though the cabinet doesn't become organized immediately, which makes sense because the robot's still given tasks to do, it's being told to load and unload the cabinet, it doesn't have time to completely organize the cabinet. Over time, as the robot loads and unloads bowls, the environment becomes easier to use. The cabinet becomes more and more organized over time because the robot is biased towards these sorts of solutions. What we can also see is that, in fact, if the robot were given sufficient time to prepare the environment, if it were given some time in advance to organize or prepare, we can put the world in a state where it is indeed organized right off the bat. So the robot can then align all the objects in this cabinet and organize the state of the world so that everything is better from the beginning. The thing is, though, that if you organize the environment but then behave in a way that is myopic, the cabinet becomes messy again. Because eventually the robot's going to start putting back objects in a way that lead to this disorganization. So this graph, I love this graph. This is like exactly what we wanted to show, was this idea that if you start messy, our thing makes things organized. But if you start organized, not using our approach makes things disorganized. And so this is really good emergent behavior. Remember, we're not telling the robot what organized looks like. This is just a thing that comes about because the robot now understands what good behavior looks like in these sorts of environments. So we do this same sort of thing on a physical robot. So we have some physical experiments as well, where we're doing basically the thing that I showed you in the simulator, but on this physical fetch robot, because this is how you get papers published in the robotics domain. But what we show here is that our learning-informed approach knows how to load the cabinet so that these future tasks will be easier. And so it sends a small additional immediate cost, but significantly reduces overall planning time or overall plan execution time, because planning time is ambiguous. It could mean how much computation you spend. It could mean how much time the robot spends. I mean how much time the robot spends, but also the amount of additional computation is very, very low because learning is relatively cheap these days if you have any kind of GPU. So in conclusion for this project, we have demonstrated this idea of anticipatory task and motion planning, an approach that integrates task and motion planning work on how to do this sort of manipulation planning, but using our learned model biases the robot towards solutions that end up making the world easier to use as time goes on. I really envision that this idea of anticipatory planning will give rise to many common sense-like behaviors, all sorts of things like tidiness and organization, but also things that social agents exhibit. So you share the world with people. You don't want to be obtrusive. You don't want to be in the way. You don't want to make a mess for somebody else either. And so this idea of having robots that are also courteous, that tidy the world, not just because they need it, but because other people that they share the world with also need it, can all be emergent behaviors from this way of looking at the world without the need to directly reason about what other agents in the world are going to have to do. And so that's some ongoing work. We have some cool experiments. I don't think it's going to get submitted to ICRA, but we're working on it right now. And if people are interested in talking about that, please do let me know. I'm really interested in incentivizing this because it's a very difficult family of behaviors to talk about in any other way. That most of the time when people think about tidiness or courtesy or common sense, they're pretty amorphous and don't have very precise definitions. This is a way of incentivizing those sorts of behaviors from a very mathematically grounded formulation that says, I think that courtesy, that tidiness, and organization are all emergent properties of trying to keep the world easy to use. And I'm really excited about that idea. So the key takeaway from a lot of my work as I wrap up today is that many of our advances are made possible by the integration of learning and planning. The idea is to plan using what you know about the world, and then use learning to estimate statistics about what you don't. And so many of these advances are made possible by the integration of learning and planning, which includes things like long horizon task planning under uncertainty, this idea of introspection and interpretability despite uncertainty, and then the more recent and ongoing direction that is anticipatory planning in my lab. The robot, by understanding not just what it needs to do right now, but how the world may need to be used later on, can make better long horizon decisions in environments that persist, that are not just reset between tasks, as a lot of robot planning problematically focuses on. The vision in my lab is this idea that robots that are performant, that behave well despite uncertainty in space and time, that are trustworthy, that non-experts can understand and correct behavior when necessary, and that are reliable, that have guarantees on plan completeness, and that can self-audit and improve during deployment through interaction with the environment. Nearly all of these are challenging because acting well requires imagining the future or some part of the world that the robot cannot see, making planning directly this impossible, onerous task, and something that we use learning in order to try and be able to fill in. That when the robot is missing knowledge, it uses learning to make predictions about what might happen and then use that experience to make better decisions despite this complexity. So also be sure to check out our code. There's like a lot of code in my lab and like a lot of things I'm really excited to share. We have Docker containers. It's really easy to download and build the code. If you have an NVIDIA GPU, you can reproduce 6 papers worth of experiments from this one repository with a single line of code. I wouldn't recommend it. It takes a very long time, but it's a thing that you can do, and I'm very, very happy with that. So with that, thank you all. It's really great to be here. Obviously, I'm around for questions for a little while longer. Thank you, Lucas, for hosting me. And with that, I can take questions and acknowledge my collaborators and funding sources. Thank you very much. All right.
Thank you a lot, Greg, for your presentation.
Yeah.
So many interesting things. I'm going to open for questions. Whoever wants to ask questions, people on YouTube, you may not have, I don't think we have chat, but if you want to ask questions, feel free to send me via email or however you can contact me, and I will ask Greg the questions.
Yeah. So people can also follow up with me after the fact if they don't want to ask immediately. I'm bad at asking questions in real time. So just feel free to send me messages.
So questions, things that anyone wants to ask.
Lucas, I know you were already talking. I mean, you asked this question about like where the actions come from. This is a thing that we think about a lot. I actually have a collaborator at Brown as well, he and I are working on some of this breakfast preparation stuff. He does a lot of this skill learning work. So like one of his big claims to fame, he publishes iClear all the time, actually. But he does a lot of this idea of like, how can we show a robot a simple skill and have it then understand how to use that skill in lots of different contexts? So, like a lot of their early work and like learning skills and a lot of the, modern machine learning stuff has made even better.
Yeah.
Oh, great.
It's awesome. I think Paulo has a question.
Yeah.
Okay. So first of all, thank you so much for the presentation. It was phenomenal. And great. The work you do is also very, very exciting. I mean, to us, but also, I guess, to the rest of humanity too.
That's the hope, right? But thank you. Yeah.
And I'm pretty sure a lot of the other people here were all hoping that your papers get accepted at iClear.
Well, that's great. No, I'd love to come visit. I think, again, I was telling Lucas this before. It's like, I'm not really much of an iClear person because I think about planning problems, but planning problems that really only robots have. And so I end up submitting mostly robotics conferences. But yeah, it'd be nice to come visit.
But so a lot of us work in machine learning and these days deep learning, I guess.
Right.
And a lot of the things you mentioned, they kind of resonate with what we've been doing over the past couple of years, I guess, specifically in terms of like long horizon tasks and self-improvement, right? Those are two things where, the first, chatbots that we came up with weren't very good at, but now they're pretty reasonable. So for example, math, as you said, right? Clearly we're improving, right, on math. And to a large extent, it kind of seems like this doesn't that have like a direct impact on a lot of things you're doing? I mean, these LLMs,
Yeah,
they can reason to a degree, they can plan to a degree, they have like world
right.
knowledge to a degree. Doesn't that make a difference to you?
It does. It definitely does. It makes two differences to me. One, it has made getting my work accepted to conferences harder, which is good because it makes everybody stronger. But the other thing is that qualifier, the to a degree, is the thing that makes me very nervous, right? Is I'm really interested in building these representations that even if they are less effective under many circumstances, have these guarantees of reliability. This idea that like the robot has a partial map of the world, it should be using that information. I also really, I play around a lot with these language models and ChatGPT and things, and I think it's just there's two lessons that I kind of take away from a lot of this stuff, and in different contexts. One of them is that they are getting better at math, but they are still not good at math. And as a result, I think, you look at a lot of these works that have taken, they sort of describe the whole world to ChatGPT, and they say, what should I do next? Those approaches kind of work. And actually, they're decent. The ChatGPT will give reasonable actions. But when you look at those papers and you really dive deep into like the performance metrics, they're like, we get good performance when we finish the task, and we finish the task 65% of the time. That is an unacceptable level of performance to me. We complete the task 100% of the time in simulated environments, right? The robot might fail, the perception might be bad. So I'm talking specifically about planning. And I think a lot of these works are focusing on like just the ability to complete the task. And I don't think that, and most of those works are not thinking about doing the task well. And so right now, I think we're not there, and I don't really think we're close to being there. The other section of work in this space tries to actually output code. They say they try to output things like PDDL, this planning language that I described right at the beginning of the talk. And they say if ChatGPT can write out what actions exist and how those actions change the state of the world, we can then send that to a planner, and the planner can then make the good decisions. There's two problems with that. One of them, it's like 75% reliability instead of 65, which still is an unacceptable amount of failure to me. But the other thing as well is that it still doesn't really care about performance, and the abstractions are not the right abstractions for a lot of problems. So PDDL ends up being very single robot focused, and it can't handle uncertainty in any capacity. So when I start thinking about multi-robot coordination under uncertainty, I think a lot about like search and rescue, wilderness disaster response. Like, you have fires and you have to have robots that split up and figure out how to find people and look for supplies and deliver supplies and all this stuff. That level of coordination is something that I would never expect. Or I mean, maybe I would say I can't say never anymore because ChatGPT amazes me. But it is right now, these language models are just stochastic parrots. They're just emulating what they think is a good thing to do, and they're not asking themselves whether or not it is the right thing to do. And that is a thing that I care a lot about in my work. I really think that the best scenario for me is that these approaches meet in the middle. In the same way that like a lot of like LLMs will say, "Oh, you've given me an addition task. I'm going to call Python. I'm going to use a calculator. I'm going to do these things." Like I see a marriage of these tools in the future. But in order to be able to do that, you have to have the right interface. You have to have the right abstractions. I am a planning researcher, but the thing that I think about the most is what is the right way to write down a problem? And so most of my work is in the space of coming up with the right models and the right representations. And I think it is through that work that we can come up with this interface. It was a really long answer. The short version is I don't really know. It has definitely made my life harder. And I think my work is going to help bridge the gap between the things that are best about both. Sorry. So yeah. That's my answer.
Can I quick follow up?
Yeah,
Sorry,
go
I
for it.
know other people want to ask stuff, but it's just so again, it's very interesting, and I feel like a lot of what you're seeing maps to the things that we've done. So, for example, I guess the from our side, lean would be sort of like the
Yeah,
language that we would use,
yeah,
and lately, like the models that are getting IMO golds, or they're not using lean, which is again surprising. And so the question is not so much like, do you feel like they today like these LLMs could power these robots, but kind of like it doesn't. I mean, kind of looks like they could in a couple of years. And
yeah.
to me, on the other hand, it's funny because when you start introducing the problem, what seemed to me the difference between sort of this like math analogy and what you're doing is, I guess robots have to do with like improvisation all the time. So it's as if you're trying to like solve this complicated like IMO problem
Yeah.
or a math problem, and then at some point like someone says like, oh, we're changing the rules of the games, right? Because I guess for robot, like, does that like, how do you guys deal with that specifically, right? Or is that, I mean, because you must, right? If you have like self-driving cars around, they must.
Yeah, I'm not going to touch self-driving as much because it's a very hard problem in many different ways. But I'm going to break your question into two parts. The sort of second part is about this improvisation. I think it seems like you have a lot of experience with machine learning. You know that machine learning really doesn't generalize very well. The way to generalize is to make a new problem look like the problems you've already seen. That's the role of abstraction. And in fact, that's what a lot of my work is attempting to do, is trying to ask simpler questions to get answers, to like ask simpler questions that are related to the questions I've already taught the robot to answer, and then use those answers to compose into these more complicated problems. The planning side of things, the code is capable of handling that improvisation very well. I can give my robot a larger building. The learning is still only looking at one picture at a time and saying, what's the probability that this leads to the goal? Where's the fork in this picture? All these sorts of things. And then it's the planner's job to compose all of those and come up with an algorithmic answer that's capable of handling the more sophisticated parts of that problem. So like that's on the improvisation side. And there's some amount of like, I don't know how to solve that problem. No one knows how to solve that problem. But on the other side, I think we've been, I go to a lot of robotics conferences, and there has been like there are panels every conference with like the most famous people in the discipline. Where do you think robotics is going to go? Do you think it's ChatGPT? Do you think there's no ChatGPT? And I think everybody has a different version of both of those things are necessary. And what the mixing strategy is not quite clear. But one of the things that has become, so you look at something like ChatGPT. Have you ever asked ChatGPT to try and tell you a story and then be like, no, that story is too short. Tell me a story that's twice as long. It cannot do it. Hierarchy is important, abstraction is important, outlining is important, and it doesn't know to do any of those things. The cracks are still there in ChatGPT. Even as they get better and better at like faking stories, I still don't think that like a lot of intellectual work can be replaced by ChatGPT, in part because, they're really good at doing things that are in distribution, but as you start to get out of distribution, you start to ask it for more and more complex things, they're not very good at it. And in the robotics context, what has been a really interesting lesson learned by the much more hardware-focused people in the community than me is we are out of data. So even ChatGPT is trained on like, let's say, I think this is probably a lower bound, roughly like 10% of like all the text that exists on the internet, right? There just is, and you're looking at these logarithmic scaling laws. So you go up by a factor of 2, you go up by a factor of 10, you're getting a linear improvement. We don't have more data. We don't have more text. And in robotics, the data is even sparser because everyone has a different robot. They have different hardware. They have different stuff. So think about how much text you have read in your life, and then think about how much interaction with the world you have done. And I am like a better writer than I am interacting with the world. And that's the sort of amount of data that we need robots to have. There's this thing, it's known as Moravec's paradox. It's this idea that tasks that are harder for humans are easier for computers and vice versa. So like math and whatever, we can come up with a very specific algorithm, or I say like 4-function math, like multiplication. We can make a computer, we can make a machine that does that. Picking up an object, by contrast, is something I'm much better at than multiplying large numbers, but a robot still struggles to pick up objects reliably. And so we're coming up against these problems where there have been like 1 billion years of evolution worth of data to solve in hardware, and robots don't have that. So I don't really think that my job is ever going to become obsolete, right? It's like there's still these really, really hard problems that even as we get to like 95% reliability, that's not enough. 5% chance of failure on a task that requires 50 interactions with objects will never succeed. So again, I know Lucas knows I have a tendency to ramble, so I'm going to stop. But I think I have a lot of opinions on this, and I think everyone is comfortably knows they don't have the answer. But it's not one or the other; it's both, and we don't know what that looks like. All right, do other people have questions?
I have a question.
Yeah.
I think it's about this last part you talked about the anticipatory thing. So I don't know how is the research on this part. Like, how would if we have like a robot interacting, it has to interact with other agents, maybe humans and
Yeah,
stuff. Maybe in an environment that there are humans moving around.
right.
How do they do? Do they have to like predict the actions of the humans to be able to?
Well, maybe.
What
So
are the
so there's different levels of
strategies?
this. So there are a few colleagues of mine at George Mason University that work on human robot interaction, like
Mhm.
humans and robots working as a team. There are many different types of teamwork. And in fact, like let's say like I live with my wife, right? I live with somebody, right? She and I share the world. 95% of the time that we are acting, we're not working as a team. I
Mhm.
just know that so my desk is right here, my wife's desk is right here. My desk has a few things on it. I can make my desk cleaner by taking everything and putting it on her desk.
Yeah.
You laugh, but that's a thing that robots do. In fact, robots are
Right.
very clunky and intrusive, and I argue that part of it is because of this lack of understanding.
Mhm.
I'm not interested in real-time teamwork. I mean, I am interested because I'm curious and I love everything. I love all this research and stuff. But I'm not trying to solve the real-time team problem. I'm trying to solve the problem of I tell a robot to clean the bedroom and it doesn't make the kitchen dirty because
Yeah.
it's following one task and it's making other tasks harder. And in the case of these shared environments, it requires not an understanding of what I'm going to do next, but the types of things I might do next. And that's actually the thing that makes this problem even harder because it's not just a prediction of what action I might do next, it's an understanding of how I interact with the world in general, and then plan according to that distribution of things that I might do. So it's like the statistical version of the action prediction problem.
Right.
But yeah, that's still ongoing. I'm actually
Yeah.
collaborating with that other human robot interaction researcher because she works on teams. She thinks a lot about teams of people too. There's really
Mhm.
interesting things. So there's a lot of work in like robots and communicating with humans, robots that announce, I'm going to do something. And then the human says, okay, the robot's going to do that. I'll do this instead. When they're like building furniture or something like that, right? Simple tasks.
Mhm.
What's really interesting is that for teams of humans that work together really well, when humans get busier, they talk less and they anticipate more. So what happens is if I don't know if you cook with anybody, but if you're cooking with someone and you don't have much time, you got to cook fast, right? You will go out of your way to like chop a vegetable that the other cook needs. That's a thing
Yeah.
that happens when we get busy. We understand what the task needs, we understand what other humans need, and we just start doing those things. That's a thing,
Mhm.
that's a capability that just robots very much just don't have. And I'm really interested in coming up with the right
Yeah.
abstractions that can combine planning and learning to make that sort of
Mhm.
decision making both reliable and effective. So she and I have been talking about this a lot. I'm really interested in it. Humans exhibit this sort of behavior all the time because it's very effective, but we don't know how to make robots do it. It's really cool
Right.
stuff. I'm really excited about this anticipatory planning stuff.
I think I have another question,
Yeah.
maybe. So, I think another aspect, like you're dealing with hardware and everything,
Hmm.
and like the robots have a lot of sensors and stuff. You use
Yeah.
vision and a bunch of stuff. And how do you deal with like maybe a sensor breaks or like there is low light and you can see very well? Like, can you put these things in the statistical model to take into account like the state of a sensor or something?
Yes. I don't, but other people
You
do.
know.
So
Okay.
so if you look here, so you see this on the top, there's
Mhm.
like QR codes.
Yeah.
Like it looks like a QR code. That is a visual marker. This is the
Right.
thing the robot looks at, and it doesn't have to do object detection. It detects those and it says, aha, I
I
know what the
see.
green block is, right? So some
Mhm.
of the time we're like faking perception. We have newer, let me see if I can find the new video. Um, we have some newer videos where we're not doing any of that, and it's on my like favorite hardware platform. But there are people that do this. So one thing that's really uncertainty is very, very difficult. There are many different forms of uncertainty. I've talked about a few of
Mhm.
those, but the idea that there is, I don't know, object uncertainty is very, very hard in particular. Is this idea
Right.
that I see an object and I don't even know what that object is crazy. So there are other people that do that handle this sort of uncertainty. I haven't even looked at all these videos. This came from my lab like yesterday. But this idea, okay, these are like my student. Okay. So here you could see this is one of our Spot robots. It's a very expensive robot. You see this like kitchen and an oven. It's moving around, it's looking for objects, and it's picking them up. So right now, this again has this sort of marker on top. It has a camera built into the gripper. This is a laser that it's using to scan the map of the environment. So it's moving around, and then, oh, the video ended. But there's videos, I know there are videos of it picking it up, right? Okay. So again, so this is kind of an answer to your question, right? So the robot is always like sensing the world and stuff like that. I have a whole rant about turning on the lights. I'm not going to do it because but so turning on the lights is so cool. It's a thing that when you have perfect perception, you never do. It's an information gathering action. It is an action specifically take to make your information stronger and better. In fact, that problem more closely relates to the map finding problem that I described earlier. Just like when you look for a map, you can take information. Sorry, the internet's kind of slow to load this video, but it does pick up the cup and it moves it to where it needs to be. Hardware is really hard. I am kind of not a hardware person because like focusing on planning is hard enough. And I let my collaborators help with that. So this is work done with collaborators at Brown University. And they're experts in hardware. So that's, But yeah,
Nice,
good question. Really hard problems. You can't solve everything.
Yeah, I imagine. Thank you.
Maybe one final question, if anyone has another one, just so we don't.
Yeah, no pressure. Like you can hear I'm losing my voice.
I think there's something fascinating, and Daniel kind of alluded to this point, but there's something fascinating to me, which is like the fact that, in some sense, politeness, organization, and other properties that we would think of just, it's just a code of conduct that it's good behavior in some way, or there's some reason, but actually they're intrinsically mathematical to the solution and to the planning strategy.
Yeah, I agree. So that has been, I think, the biggest upshot of this work was that most people in robotics don't think that way. They're trying to incentivize courtesy through imitation. They show humans behaving in ways that are courteous, and they use that data to try and train a model that then exhibits similar behavior. I am very interested in thinking about courtesy as a mathematical optimization problem. But keep in mind that this will not give rise to all forms of organization and courtesy. For example, people have asked me like, oh, you're talking about organized. I like to keep my apartment feng shui. Like I like to keep, this object facing the windows and all that stuff. The robot's not going to know things that are aesthetically pleasing. It only knows preferences that are cost-based. And so, I don't know. Okay. Anyway, I'm being my own adversary right now. It's so frustrating because I keep getting like people who look at this and they're like, oh yeah, but does the robot understand art? I'm like, no, of course not. Like, that's not the point, but one of the things that we really showed, and I think this is the thing. So this paper is, sort of confidentially, it's undergoing rebuttal right now. And the reviewer is basically like, what about generalization? What about changing the task and motion planning solver? Like, what about this? What about that? What about that? And I'm like, our answer to this is basically, no one is thinking about this problem the right way. Like all of your questions are predicated upon like this idea that all of these other things matter more, but they're separate. They're like separate pieces of research, right? So I'm really interested in this insight of like, what about human behavior can be written out as cost? Because I think those are the things that robots should do. Because I don't think that robots should replace, like, I don't want robot poets. I don't care. Like humans are good poets and they should be poets. And I'm really interested in trying to figure out what parts of our preferences, what parts of our interactions are social, what parts are structural, what are both. And so this is our initial answer to this. We have other work actually in like home scale environments. So thinking less about task and motion planning, but like, where do you put all the objects? Right? Like, how do you organize a house? If you know what types of things the human needs to do, the robot can say, here's how you need to organize this house. And that's like really cool. And it can do it incrementally in real time, right? So I don't know. There's lots of really interesting questions here. And I by no means do I know the answers to all of them, but I'm very interested in this continued exploration of why do humans behave the way that they do? And I think it also simultaneously addresses this question of why do people not like being around robots? It's because they're rude. Like that's one of my answers. It's just like even when they succeed, they were like, I don't know, Lucas, you gave a thumbs down that this cabinet was successful, but it succeeded at the task, and most people overcome that problem by making the task more specific. But we would call a human that did this an idiot. It's like we'd just be really human. We should hold robots to the same standard. So I don't know. That's my answer.
Awesome. Well, if there are no further questions, I want to take the time to thank Greg one last time. Thank you so much for doing this. This was an amazing talk and great chance to learn more about robotics, planning. As Greg said, if you didn't have the time to send questions, his email was on the slides. Do not confuse him for Greg or for G. Stein.
For G. Stein,
he told me that people email that a ton. So
true.
Please remember the J.
I'll put it in the chat. There are 2 Gregory Steins at George Mason University, and our emails are very similar.
Yep. There is a J in the middle. So
yes, my middle name is Joseph. Don't forget it. So gjstein@gmu.edu. Do send me a message. As you can imagine, you can see I like to ramble a lot. You will get a long email. So send me a message. Anyway, thanks for listening to my rambles. Thanks for listening to my talk. It's really great to meet many of you. And do, reach out if you have any questions. Okay.
Yeah. Thank you so much.
Thanks a lot.
Thank you. And thank everyone for being here. As a reminder, we will be having our next seminar in 2 weeks. So we will have Andre Massimo, I believe, talking to us directly from NVIDIA. So yeah. We'll see you all in 14 days. Bye, everyone.
Great. Have a good one, all.
Thank you, Greg.
Thanks, Lucas. We'll talk.